My name is Harrison Williams. I'm a postdoc at Virginia Tech. I'm going to be talking about some of our work on NVM-invariant software-only intermittent computation. This work is a collaboration with my former lab mate Simon Maud, who is now at Amazon, and my doctoral advisor Matthew Hicks. So this work targets mobile and IoT deployments which are reaching massive scales. Market estimates suggest that there will be over 25 billion such devices by 2030, the vast majority of which will be tiny resource-limited sensor nodes. They'll be deployed in all sorts of massive scale applications ranging from industrial IoT to wearable and implantable medical devices to environmental monitoring for smart cities. Now, unfortunately, at these massive scales, battery power is a complete non-starter for economic, design, and even ecological reasons. As a result, there's been growing interest in the field of batteryless system design. These are systems that completely remove the onboard battery and replace it with an energy harvesting circuit, as well as a short-term energy supply, typically some kind of supercapacitor. And these systems have a lot of system-level benefits. They can be built smaller, cheaper, and run for longer than their battery-powered counterparts. Unfortunately, they also introduce a number of device-level challenges. They have to cope with constant and frequent power interruptions, deal with severe energy constraints, and also deal with bugs that arise as a result of their intermittent execution. The diagram on the bottom right here shows a simple diagram for an energy harvesting system. We have the energy harvesting circuit itself, which charges up a supercapacitor up to some enable voltage, in this case on the bottom left, 3.3 volts, at which point the system turns on and begins draining the capacitor down to some disable voltage, in this case 1.8 volts, to do a small quantum of work. So the basic operating mode for these intermittent systems is short bursts of operation punctuated by longer recharge times. And the basic challenge for these systems is sustaining long-running computation across these power cycles. How do we finish some software task that takes more than one power cycle to complete? And the basic approach is to use this idea of checkpoints, where right before we lose power, we store all of our volatile state in some sort of persistent store. Next time we get power, we can pick up where we left off by restoring that state into our volatile memory and continue execution. So we can run arbitrarily long software tasks across arbitrarily short power cycles. Unfortunately, these rapid writes to persistent memory expose any sort of performance limitations of the non-volatile memory on the system. Extra unfortunately is that the most common non-volatile memory available on these IoT scale devices is flash memory, which is particularly poorly suited for the demands that intermittent computing places on it. Writing to flash is particularly high power, and it's also endurance limited. The flash on these IoT scale devices is typically rated for 10 to 100,000 write cycles before it's worn out. And at the rates that intermittent systems typically need to write checkpoints, this results in a system lifespan measured in weeks to months, rather than the decades that we would like these systems to be deployed for. So as a result, researchers have mostly moved away from flash memory into more esoteric, relatively young memory technologies like ferroelectric RAM, magnetic RAM, or resistive RAM. These are technologies that, for the most part, overcome the performance limitations of flash. Writing to these memories is not significantly more power intensive than writing to SRAM, and they don't have any sort of practical endurance limitation. The major problem with these memories is that they have strictly very limited commercial adoption, very limited availability, so it's difficult to build systems out of at least commercial components using these memory technologies. We did some work overcoming this in 2020, building a system called Total Recall, where our goal was to enable intermittent computing on these flash-based systems by leveraging the observation that the data retention voltage of SRAM is typically far below the minimum operating voltage for the microcontroller that it's actually integrated into. So typically on the systems that we saw 100% data retention down to about 400 millivolts, where the entire system stops running at about 1.8 volts. Combined with the fact that these systems by construction have very large capacitors holding the supply voltage up, we can see full data retention in the SRAM itself for hours to days, which in the vast majority of cases is more than enough time for the system to charge up enough to hit its enable voltage and continue execution. This means that instead of writing data from our volatile SRAM into some truly persistent store, all we need to do is calculate a checksum over all of the SRAM to ensure that we didn't actually lose any data while the system was off. So our checkpoint is reduced from copying data into persistent memory down to a checksum calculated over all of SRAM. This works for basic software tasks, but unfortunately the cyber-physical systems that typically represent energy harvesting devices need to interact with the physical world because in many cases they're sensing or actuation systems. This requires interacting with peripheral devices. which may require some sort of atomic operations that's not easy to split across power cycles. So on the left here, we have a simple code snippet for a sense, compute, and transmit application. The software portion of this code can be arbitrarily split across power cycles. If we lose power in the middle of, say, our compress operation, all we need to do is take all of our volatile program state, put that into some sort of persistent store, and then when we have more power, we can bring that back out of the persistent store and continue execution, sort of arbitrarily, wherever we lose power. This isn't the case for many peripheral operations. For example, if we try to split a radio transmission across power cycles, it's going to fail. This is an atomic operation that has to complete in one power cycle. This means that to get this operation running correctly on an intermittent system, if we lose power in the middle of the operation, we need to roll back execution. We need to re-execute parts of the code. Now, this rollback and re-execution introduces a number of correctness, performance, and programmability challenges that didn't exist under the checkpointing model. To overcome these challenges, researchers have introduced this idea of task-based programming models, where we take our sense, compute, and transmit application, and the programmer logically decomposes code into tasks. So we might have a sense task, a compress task, and a transmit task. The compiler then inserts code for checkpointing at the boundaries between each of these tasks, so that if power is lost during one of the tasks, the system automatically rolls back to the beginning of it, and correctly re-executes whatever code needs to be re-executed within that task. Another advantage of this approach is that there's no longer a need for any sort of hardware energy monitor. The software is sort of inherently hardened to intermittent execution. This is an advantage, as we'll see later, because energy monitoring is often a significant portion of power consumption in these already energy-constrained systems. Now, these task-based models have their foundation in storing a known good state that they can reliably roll back to in true persistent memory. And the first problem that we observe is that this is incompatible with SRAM-based checkpointing using checksums. To get an idea of why, let's try naively applying the checksum-based approach to our task-based model. We'll calculate a checksum over all of SRAM at the beginning of our compressed task and enter it as normal. Unfortunately, the first instruction that we execute in the compressed task is going to make some modification to the volatile memory that we just calculated the checksum over, therefore invalidating the checksum and losing our checkpoint. So the question that we set out to answer is, how can we apply this idea of in-place SRAM checkpoints to task-based intermittent systems and bring these execution models to devices that don't have high-performance persistent memory? So to that end, we introduced a system called CAML, which is based on the idea of two mixed volatility SRAM worlds. We leverage the observation that by calculating a checksum over parts of SRAM, we can essentially arbitrarily render different parts of SRAM non-volatile. We can reliably recover them after a power cycle. So if we render only part of SRAM non-volatile, we can use the volatile section to store our working data that our tasks operate on, and we can use the checksum back section as our known good rollback state for when tasks are interrupted. The main design considerations when we're building this system are first that SRAM is very scarce. Compared to non-volatile memory, it's relatively low density. One of these systems might have 128 or 256 kilobytes of some sort of persistent memory, but only 2 to 4 kilobytes of SRAM. This means that we need to minimize memory overhead if we're going to store all of our information inside of SRAM. Second, calculating a checksum over any sort of non-trivial section of memory is very expensive. It's much more expensive than writing to these high-performance memories. This means that we need a model that minimizes writes to our non-volatile SRAM world so that we don't need to recalculate the checksum too often. So to get an idea of how we built CAML, it's important to first have an understanding of how a true persistent memory-based task model works. So we have our non-volatile memory with two buffers containing our program data. On the entry to a task, the compiler will insert entry code that first privatizes this, any data that the task is going to work on into a third working buffer inside of volatile memory. We then enter the task where the task works on that private data and eventually completes. Now we have this updated state that we need to recommit back into non-volatile memory. So this works, but it has a couple of drawbacks. First is that there are 3 copies of our working data at any time, so we have high memory overhead. There's also high data movement overhead. On every task boundary, we need to move data from persistent memory into our volatile store, and then from our volatile store back into persistent memory. Let's look at how CAML does it instead. So we have our SRAM split into 2 buffers, A and B. Buffer A here represents our known good rollback state, and buffer B is our working state. Instead of privatizing data from a persistent store into some working area, CAML tasks work on data in place. So CAML tasks directly access variables stored in the volatile section of SRAM. Once the task finishes operating, buffer B contains the updated state that we would like to lock in to ensure to lock in our progress. So we calculate a checksum over the newly updated state in buffer B. So we've rendered B essentially non-volatile. The last thing we do is we do an atomic buffer swap that renders buffer A the new volatile working state, so that the transmit task, the subsequent transmit task, is going to work on buffer A and use buffer B as the rollback buffer. After the atomic swap, the last thing that we need to do is a partial update, moving all of the updated variables from buffer B into buffer A, so that the transmit task has all of the updated state that we need. So by doing this, CAML effectively eliminates data privatization, which is the major source of overhead between tasks. We've gone from 3 copies of our working data down to 2, and we've eliminated the data movement associated with moving data around between buffers, down to the bare minimum that we need to do. So that's one half of the story. That's how CAML works between tasks. Within tasks, CAML efficiently rolls back state following a power failure. So we have a toy example of a CAML task here on the right, where we write the temp and result variables and we read the x and y variables. On the left, we have a table of the value of all these variables. Say we go through one execution of this code so that we update the temp and result variables, but we lose power right before we're able to commit any of this to any sort of persistent store. This means we roll back to the beginning of the compute task and re-execute it. Unfortunately, this rollback and re-execution introduces a semantic bug because this task is non-idempotent. Its ultimate outcome depends on the number of times we execute it. And we can do some brief compiler analysis to figure out what exactly the problem is. Temp, x, and y all undergo fully idempotent accesses. X and y are only ever read, and temp is written the same value every time we execute. The result variable, on the other hand, undergoes a write after read access, where essentially we increment it by the value of temp every time we execute this. And this line of code is what renders this entire task non-idempotent. To overcome this, on rollback, CAML identifies all of the write after read variables that need to be rolled back to their initial state, and does so when the system restarts and goes back to the beginning of the task. One interesting thing to note is that we only need to roll back specifically the write after read variables. The system doesn't need to be rolled back to the true initial state that the global state was in before the task executes. So we don't need to roll back the temp variable because it's always going to be written to the correct value during the actual task. On subsequent executions, the system is always going to have the same result, that which is consistent with continuous power operation. So the CAML compiler identifies the minimum set of variables that we need to roll back to ensure correctness. We implemented and evaluated CAML on 2 target platforms, both MSP430-based systems, which are representative of typical energy harvesting class devices. We looked at a G2955, which is a flash-based device, and an FR6989, which is an FRAM-based device, one of the high-performance persistent memories I talked about earlier. We evaluated the system on both real hardware and in simulation. We evaluated both of these systems on an RF energy harvester, and then we also simulated CAML's execution in a modified software simulator that gives us better instrumentation to determine CPU cycle overhead, number of times that we hit different commit points in the program, etc. We evaluated CAML against total recall, which is our SRAM-based checkpointing approach, as well as prior task-based systems that are based on this high-performance persistent memory. We evaluated CAML and all the baseline systems across 8 benchmarks for correctness and performance. It's not noted here, but we implemented all of CAML's compiler passes using LLVM. The first takeaway is that CAML enables efficient and correct SRAM-based intermittent execution. Shown here on the left is the number of power cycles to complete a given software load for the baseline total recall system compared to CAML. We see that CAML realizes a 3 to 5x performance improvement over total recall using software-only intermittent computation. Because CAML eliminates the need for on-chip voltage monitoring, more of the energy that the system is actually harvesting can be directed towards software execution. Like I said before, that voltage monitoring that's necessary for checkpointing approaches can represent a significant portion of energy consumption on these constrained systems. In terms of correctness, we have our 3 benchmarks on the right, where we interact with different peripherals in different ways to exercise how total recall and CAML interact with them. Across all these benchmarks, total recall fails to either reconfigure peripheral devices or incorrectly interrupts atomic operations and fails in various ways. On the other hand, Camel provides an easy interface for programmers to correctly re-execute atomic operations and reconfigure peripheral devices following power failures. Beyond SRAM-based intermittent computing, we also isolate how Camel's differential buffer design that eliminates privatization improves all task-based intermittent systems. So on the left, we compare Camel to 3 prior task-based works, and we particularly focus on the right on how Camel compares to Alpaca, which is sort of the state-of-the-art in task-based intermittent computing, the best performing state-of-the-art. When you see that by eliminating data privatization, as I talked about earlier, Camel's buffer design outperforms Alpaca by an average of about 2x. Alpaca sees about a 300% performance overhead compared to baseline uninstrumented non-intermittent C, while Camel brings that down to about within 50%. On the bottom right, we show the number of inter-task commits, and that while Camel marginally reduces it, the majority of our overhead reduction is from eliminating data movement. So Camel not only enables this operating model on SRAM-based systems, but also introduces a differential buffer approach that improves all intermittent systems regardless of the memory technology. So in conclusion, I've talked about Camel, high-performance NVM-invariant intermittent computation, which brings efficient and correct intermittent computing to the largest class of devices today, that is flash or even mask-ROM-based systems that don't include high-performance persistent memory. Even on high-performance persistent memory systems, Camel introduces a differential buffer design that substantially improves task-based systems on any intermittent platform by minimizing data movement overhead. In the paper, we go into more detail on memory consumption of each system, cycle overhead for different checkpointing and commit methods, different integrity check methods for our SRAM, and more. You can find the paper at our group research website or at my website shown here on the bottom right. So thank you, and now I'm open now to any questions that you might have.